So we've got a 12-step color wheel. We've got primaries, those are the things that we use to mix. We've got secondaries, those are the result of mixing two primaries. We've got intermediates, which are not tertiary, but instead an intermediate is the result of the mixture of a primary and an adjacent secondary, and I have to say adjacent because otherwise I get Cmyk. And we also do have a thing called tertiaries, but they don't show up on our color wheel. A tertiary is the mixture of a secondary and a secondary. Wow. Now, not only did they lie to you about the color wheel, they lied to you about what a primary color is, because there's actually multiple primary colors. With pigments, most of the time, we are talking about red, yellow, and blue as our pigment primaries. But we also have RGB, so R red, G for green, and B in light. So when we are mixing light, like your computer screen is now, we are actually doing what's called additive color mixing. And this is what Newton was playing with when he was playing with his prisms. He was bending light through a prism to split out, refract out all of the different colors of the rainbow that are contained within visible white light. With additive color mixing, my primaries are red, green, and blue, and they mix together. And if I mix them all together, eventually I get white. So I can create all the different colors that you see on your television screen, on your PC, on whatever. Phones. You kids these days with your phones, they're going to have an RGB color system. When we're mixing paint, we're going to have subtractive color mixing. And one of the things that is important to know with subtractive color mixing, no matter which primaries you're using, is all subtractive color mixing, mixing colored things, will lose color because you don't have pure color like you do with light. So when I mix red and yellow, I might get a pretty good orange because the chemistry involved is such that I'm probably mixing cadmium red with cadmium yellow, and therefore I'm going to get a pretty good orange. But if you've ever tried to mix, say, cadmium red light with cerulean blue, you ain't getting purple. You're probably getting a gray. What we're going to do then is understand that subtractive color mixing, in theory, goes all the way back to black. Dun, 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 dun. Dun-dun-dun. But what actually happens is that because subtractive color mixing has less than pure combinations of pigments, we're going to see that you're going to lose color really fast. This is true when we're using red, yellow, and blue as our primaries, but it's still true when we switch to Cmyk, which is also subtractive color mixing. So the things that come out of your printer, what are also known as process color, don't use red, yellow, and blue because we know that red, yellow, and blue creates too many failures, and we get slightly cleaner mixtures, though they still lose color, when we are mixing Cmyk. The Cmyk stands for C for cyan, M for magenta, Y for yellow, and then the K is for the black, because we have to have a separate black in our printer, because even though color theory tells me that if I mix the three of them together, I will get back to black, dun, 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 I don't actually get back to black, I get Cmyk. So I have to have a separate Y. Does it have to be K for black? Well, one, because the American society is still fundamentally a white supremacist society that subjugates people. It's because B was already taken by blue over here in the RGB. But also that racism thing too. So we're going to have K as part of our Cmyk, cyan, magenta, yellow, K for black. They're still subtractive color though. It's still going to lose color. This is why when you print out the picture you found on the internet in RGB with your printer that is Cmyk, it doesn't look as good. So you go on the internet to do research and you find the person of the appropriate gender to your preference that is hot, and you try to print that out so that you can carry I don't know, Captain America with you always. Chris Evans is very pretty. What you're going to wind up with is something that actually loses color as we move from additive color mixing to subtractive color mixing. We have actually mapped this out. We have figured out that what we have here is a representation of a chart that shows all the colors that your eye can see, which is a lot more than we can capture with color film. So when I'm looking at color film, I can only capture these colors. So the luscious red of Chris Evans's lips doesn't get captured by my film, which is sad. But also, when I look at that film and I process it and I digitize it and I look at it on my monitor, I'm getting a completely different set of color. Now, there is a lot of overlap. Color in this area can be captured by both color film and my monitor, but there are going to be some colors that my monitor can show that color film can't. And there's going to be some colors that my color film can capture. It didn't get all the way to the beauty of Chris Evans's lips, but we still got some good lippage here, except then I lose even more when I go to my color monitor. If I print on regular typing paper, I just get this. Look how gray and blah they are. So I have to spring extra for coated stock, the fancy, it's got paper with plastic on top of it so that the ink sits up a little bit better. I can get more intensity of color, but I'm still pretty gray compared to all the different kinds of colors that are out there in the universe. So all of our art systems are going to fail to capture light as well, which is why people make digital art. That plus they grew up on anime and they're just, stoned.